Welcome to the Architecture of Creation, a deep dive into how transformers and diffusion models have overcome legacy AI bottlenecks to fuel the current generative boom. The AI boom rests on two mathematical pillars. First, the transformer in 2017 solved problems related to sequence and logic. Second, diffusion models in 2020 became the standard for image synthesis by mastering the generation of high-fidelity, continuous spatial data. Transformers solved the sequential bottleneck of earlier models like RNNs. While legacy models were blocked by recurrence, transformers achieved an O1 path length, improving information retention over long distances and enabling native parallelization for better hardware efficiency. The breakthrough came with the attention mechanism. By eliminating recurrence, parallel processing was enabled. To maintain sequence order, absolute position is mathematically injected via sine and cosine functions, known as positional encoding. Self-attention relies on query, key, and value components. The query looks for context, the key contains index tags of other tokens, and the value holds the extracted semantic meaning. Multi-head attention processes these simultaneously from multiple perspectives. Generative models face challenges with continuous data. GANs suffered from mode collapse and training instability, while VAEs produced blurry, low-fidelity outputs. This created a missing paradigm for stable, high-fidelity spatial generation, setting the stage for diffusion models. The diffusion mechanism involves two steps. The forward process incrementally injects Gaussian noise until all structure is lost. The reverse process, a neural network, incrementally strips this noise away, guided by a score function to reveal a new generated image. In the generative arena, diffusion models currently represent the state of the art. They offer high training stability, top-tier generation quality, and high flexibility in architecture, surpassing the limitations of GANs, VAEs, and normalizing flows. The mathematics of noise includes three main paradigms. DDPMs use discrete steps to predict noise transitions. SGMs estimate the score function with increasing noise scales. Score SDEs generalize this to continuous time, unlocking powerful numerical solvers for sampling. To overcome the slow sampling bottleneck, engineering solutions were developed. SDE-ODE solvers mathematically bridge trajectories, reducing denoising steps. Truncated diffusion injects priors to skip the pure noise phase. Knowledge distillation trains a student network for near real-time generation. Diffusion models adapt to various data structures. For discrete data like text, they use absorbing state masking. In computational chemistry, models use equivariant Markov kernels to handle invariant graphs. For planetary data, they respect underlying geometry using geodesic random walks on manifold structures. The multimodal engine converges the transformer planner and the diffusion generator. The transformer parses the text, creating a high-dimensional text embedding vector. Cross-attention mechanisms then force the reverse diffusion process to align the generated image with the transformer's extracted semantics. Advanced conditioning controls the chaos in generation. The RPG framework allows LLMs to act as spatial architects, directing object placement in specific subregions of an image. Edit World enables world-instructed editing based on physical world knowledge, leveraging LLM reasoning to modify imagery. The diffusion core has expanded applications far beyond 2D art. It serves as a universal mathematical solver across computer vision, natural language, audio and temporal data, and interdisciplinary science handling complex multidimensional data distributions. The future frontier involves three areas: unified foundation models, which handle text, image, and video within a single latent space; exact likelihood bounds for accurate estimation without sampling degradation; and reinforcement learning alignment, integrating human feedback directly into the diffusion process.